Alright folks, so this part of the chapter 2-2 is all about molecular bonding. So two or more atoms combining to form molecules, and how they combine is called molecular bonding. So remember that the atom is the basic unit of matter. All matter is composed of atoms, and then we put these atoms together in different ways. And for example, you can have pure substances, and the pure substances come in two different forms. You can have compounds, which have a consistent ratio of atoms, like H2O. There's always two H's, there's always one O, that's water, H2O. Like C6H12O6, that's sugar. There's always 6 carbon atoms and 12 hydrogen atoms and 6 oxygen atoms, so that's another compound. But another form of a pure substance would be a single element composing something like diamonds or gold, and gold is the example here. So gold on the periodic table is Au, but of course this brick of gold that you see here is not one Au atom. You wouldn't even build, I mean, you can't see that. So what is this? Well, it's, I wouldn't even want to guess how many atoms are in there, but trillions, quadrillions, however many moles of gold atoms are in this, but it's purely gold. And diamonds would be similar, it would be purely carbon, etc. If you're not a pure substance, then you're a mixture. And there's a couple different types of mixtures here. We have homogeneous mixtures, like the milk in your refrigerator. Well, the milk in your refrigerator until it sours. After it sours, the acid that is produced causes coagulation, and it's no longer homogeneous. You actually have coagulation of some of the proteins and stuff in it. You have curd, in other words. But a homogeneous mixture, like this sugar tea, as long as there's not too much sugar in it. Why do I say that? Because if you put too much sugar in it, it won't go into solution, and you'll have a layer of sugar on the bottom. Well, no, it's no longer homogeneous, it's heterogeneous. But typically speaking, most of us drink tea with a couple spoonfuls of sugar, and we stir it in, and it's homogeneous. The thing with homogeneous mixtures is, if I took a sample from right here or a sample from right here, it's going to be the same solution. It's going to be tea if I drink from here, and it's going to be tea if I drink from here. With heterogeneous mixtures, that's not true. If you had heterogeneous mixtures of some food, if you took a bite from one side versus the other side, you would get two different flavors. This heterogeneous mixture they're showing you is marble, and depending whether you sampled from here or from here, you get different substances. So it's a heterogeneous mixture. So that's how we look at matter. Some elements will gain or lose electrons. Now remember, the atomic number is the number of protons, and if you're going to remain that element, you can't change the number of protons. Carbon always has 6 protons. Nitrogen always has 7 protons. Oxygen always has 8 protons. So without changing the number of protons, that element could lose or gain electrons. And how that works is this. If I have sodium at ground state, put a little superscripted 0 there, meaning at ground state, and I lose an electron, I lost, now at ground state it has equal numbers of protons and equal numbers of neutrons. I'm sorry, not neutrons, equal, the number of protons and the number of electrons are equal. That's why it's at ground state. There's no overall charge. But if this sodium loses an electron, it just lost one of its negative charges, and now it has one extra proton relative to electrons. I mean, it hasn't really changed the number of protons, but it has more protons than electrons now, one more. So now it's sodium plus charge. This is actually the most stable form of sodium. Sodium in the ground state will burn underwater. It reacts violently. It can even be explosive. Matter of fact, we only store sodium in the ground state in the chemistry lab. I think they submerge it in either glycerol or maybe some lipid oil or something. It's submerged in something so it doesn't react, and you can't put it in water because it will react with water. Whenever you gain or lose electrons, and by the way, let's do this. Chlorine in ground state, put a superscripted 0 there. When that gains an electron, now it has one extra electron relative to protons, and it becomes chloride, which is negatively charged. And the positively charged atom is a cation, and the negatively charged atom is a anion. So you have cations and anions. Notice you could lose 2 electrons, and you could be 2 plus. So these are how you make cations and anions. You don't change the number of protons, you gain or lose electrons. All right, so that's ionization. Cations and anions. Now, ionic bonding occurs after ionization occurs. So what happens here is this. The sodium atom will lose an electron. It just lost an electron. Right here, it's losing that electron. Because of that, the sodium becomes positively charged. Well, somebody has to gain that electron. All right, that electron is going to be gained by something. If the chlorine atom is in close proximity, it will gain that electron. And it'll ultimately gain an electron from somewhere anyway, because it's more stable being a chloride anion. So the chlorine gains the electron and becomes chloride. And here's the chloride anion. Here's the sodium cation. Now what happens is these opposite charges are attracted to each other. And this is called an ionic bond. So this is an ionic compound. It's an ionic bond because opposites attract. Notice they aren't sharing electrons. One loses and becomes positively charged. One gains and becomes negatively charged. And the subsequent cation and anion are attracted to each other because opposite charges are attracted. So that's an ionic bond. Something quite often is said in biology books that is untrue. And what they quite often in biology books say is that ionic bonds are weaker than covalent bonds. Well, the fact is that some ionic bonds are weaker than some covalent bonds. But some ionic bonds are stronger than some covalent bonds. So it's not that ionic bonds are weak. They're not. Well, some of them are and some of them aren't. You have to look at each bond individually and measure how many calories or joules it takes to break that bond. Some ionic bonds are stronger than some covalent bonds. But I do understand why biology texts say that. Because the solvent in biological systems is always water. I mean, we're not organic chemistry. We're not using methylene chloride or some ether or anything or petroleum. We're not doing that. The solvent is always water in biology. Because the solvent is always water, ionic bonds do tend to dissociate into their individual ions. And that's why biologists usually say ionic bonds are weak. Well, that's not exactly true. It's just that they might disassociate in the environment in which they exist. That's all. Sometimes two or more atoms will share electrons with each other. For example, this hydrogen gas that you see right here. They're sharing these 2 electrons. Those 2 electrons are shared. Notice that the way we draw a pair of shared electrons is one line. So one line is 2 electrons that are shared. So how many electrons are being shared right here? And the answer is 4, because each line is 2. So 2 pairs or 4 total. You can say 4 or 2 pairs. They mean the same thing. So you can have a single covalent bond or a double covalent bond. Covalent bond is when you share electrons between atoms. You can see triple bond. Single covalent, double covalent, triple covalent bond right there. That would be 6 electrons being shared. All right, so you have different types of covalent bonds there. Now, sometimes in a molecule, one of the atoms, and again, this is the pathetic fallacy, all right? Allow me to use the pathetic fallacy. Sometimes in a molecule, one of the atoms likes, I'll put it in quotation marks, likes electrons more. In other words, it has a greater electronegativity. Remember Linus Pauling? Remember the arbitrary scale where fluorine had the greatest electronegativity? Well, when you're sharing electrons, you sometimes have a molecule like this water right here, where one of the atoms has a greater electronegativity than another one. And in this case, the oxygen right here has a greater electronegativity. I'll put the greater than sign, than the hydrogen, which has a lesser electronegativity. I'll put the less than sign. When this happens, the oxygen attracts the electrons towards itself more often, more frequently. And the oxygen ends up having a partially negative charge. And I did poorly drawing that Greek letter. It's the small Greek letter delta. You know, the capital Greek letter delta is a triangle. This is the small Greek letter delta. I know I'm not drawing it well, but it means partial. So I write delta negative, partial negative. And the hydrogens are partially positive because the oxygen attracts the electrons towards itself more often. This is called a polar covalent bond because now the molecule has polarity. One end is partially negative and the other end is partially positive. So it's called a polar covalent bond. Versus two atoms that share the electrons equally, like diatomic oxygen or a molecular oxygen. By the way, I hope it makes sense to you why I would call O2 diatomic oxygen. Because there's two atoms, diatomic. I could also call it molecular oxygen. And that tells me that it's not atomic oxygen. I can't spell. I need to go back to elementary school to spell. Let me spell this correctly for you. We could also call this molecular oxygen because it's not O, it's O2. So with diatomic oxygen, of course, oxygen has the same electronegativity as oxygen. So they're going to share these electrons equally, and this is called a nonpolar covalent bond because they share these electrons equally. So I have polar covalent bonds and nonpolar covalent bonds. And the essence is that covalent bonds are shared electrons. All right, so that's covalent bonding. Let's look at a video of covalent bonding.
When forming compounds, atoms tend to gain, lose, or share electrons to achieve a stable noble gas electron configuration, an octet of electrons. In ionic bonding, an octet is formed by transferring one or more valence electrons from one atom to another. In covalent bonding, an octet is formed by sharing valence electrons between atoms. Sodium has 1 valence electron and fluorine has 7 valence electrons. If the 1 valence electron of sodium is transferred to fluorine, both atoms achieve an octet of electrons. By losing 1 electron, sodium has a +1 charge. By gaining 1 electron, fluorine has a -1 charge. An ionic bond is the electrostatic force that holds ions together in ionic compounds. Both fluorine atoms have 7 valence electrons. If 1 electron from each fluorine atom is shared with the other atom, then both fluorine atoms achieve an octet of electrons. This type of bond is called a nonpolar covalent bond. The sharing of electrons between atoms is exactly equal, and the electron density is symmetrical. The distribution varies according to the colors of the rainbow. The most electron-rich region is shown in red, in this case the region between the two nuclei, and the most electron-poor region is blue. Hydrogen has 1 valence electron and fluorine has 7 valence electrons. If the 1 valence electron of hydrogen is shared with 7 valence electrons in fluorine, fluorine achieves an octet of electrons. Note that hydrogen has only 2 electrons, which is the electron configuration of helium. When bonded to another element, hydrogen will have 2 electrons in its valence shell. In this bond, fluorine has a greater attraction for the electrons in the bond, a greater electronegativity. Because the electrons spend more time near the fluorine atom, the electron density shifts towards fluorine. The most electron-rich region is red. The most electron-poor region is blue. The result is a greater electron density near fluorine, a partial negative charge, and a correspondingly lower electron density near hydrogen, a partial positive charge. This type of bond, where bonding electrons are unequally shared, is called a polar covalent bond. A polar covalent bond can be thought of as an intermediate between a nonpolar covalent bond and an ionic bond.
Okay, so that video showed you basically what we just talked about. So now probably one of the most important, I don't know if I should say it like that, but it's very important anyway, polar molecules. Let me explain something before I go into water. Let me go back here. What about, do I have CO2 here? I'm looking for it. I have it right here. Okay. Oxygen is more electronegative than carbon. Okay, so you would think that this end would be partially negative and this end would be partially negative and the carbon would be partially positive. And that actually is what happens. but as a molecule, there is no polarity. Okay, so why is there no polarity as a molecule? Because as a molecule, the oxygens pull on these electrons 180 degrees from each other. So they're pulling equally from both sides on opposite sides, 180 degrees from each other. So overall, CO2 is not a polar molecule, but there are dipole moments, we call it. So there is unequal sharing here and unequal sharing here. So these dipole moments exist. But overall, as a molecule, because of its linear arrangement, it's not a polar molecule. Just wanted to point that out because now I'm going to show you a molecule where it has polar covalent bonds and it's a polar molecule, and that's water. There's 120 degrees between the hydrogen and the oxygen here. That's the angle that we have here, 120 degrees. Because this is not in a linear arrangement, all right, this is a polar molecule, and these bonds are polar covalent bonds. The oxygen attracts the electrons more strongly than does the hydrogen, and I get partially negative oxygen and partially positive hydrogens. This is very important in biology. Now what happens is, because water can do this, well, not because it can do this, because water does do this, it's not because it can, but because it does do this, that gives it a characteristic where it can bond to itself. And what that means is the partially positive hydrogen of one molecule is attracted to the partially negative oxygen of another molecule. Now these are intermolecular bonds. They're between molecules, not within a molecule. Let me be clear here, because that's usually a test question. This bond right here is a polar covalent bond, right here. This bond right here is a polar covalent bond, right there. This bond right here is a polar covalent bond, and this bond right here is a polar covalent bond. But what the heck is this dotted line? It's a hydrogen bond. It's between two different water molecules, and it's the partially positive hydrogen of one molecule bonding to the partially negative oxygen atom of another molecule. So it's an intermolecular bond. Water makes hydrogen bonds. Hydrogen bonds indeed are weak. How weak? Think of how easy it is to put your finger into a glass of water. You put your finger in a glass of water and you just broke a whole bunch of these hydrogen bonds. You take your finger out, the hole doesn't stay there that your finger produced. The water flows back together and makes hydrogen bonds. So hydrogen bonds are weak bonds, but they're extremely important in biology. Extremely important. So this is a water molecule with the partially positive hydrogens, and this is an ammonium. This is an ammonia. This is NH3. Ammonium is NH4. This is NH3. The nitrogen has a greater electronegativity than hydrogen. If you look at the electronegativity scale, nitrogen has an electronegativity of 3 and hydrogen has an electronegativity of 2.2. So the nitrogen is going to attract the electrons more closely. That makes the nitrogen partially negative. Well, what ammonia does with water is it makes hydrogen bonds. Water makes hydrogen bonds with ammonia, and you can see that here. A hydrogen bond always involves a partially positive hydrogen and a partially negative something else. Why do I say partially negative something else? In this case, it's a partially negative nitrogen. In this case back here, it's a partially negative oxygen. It's always a partially positive hydrogen in hydrogen bonding, and that's bonding to a partially negative something else. There's some other bonds that your book doesn't talk a lot about. I do want to mention them. They are called van der Waals interactions and hydrophobic forces, and you can see that right here. What's really going on here is there's no polarity or charge at all in here, but when these approach each other, like when this methyl group approaches that methyl group and that methyl group, what they do is they cause the electrons to move a little bit, and they have what we call van der Waals interactions. They're hydrophobic interactions or van der Waals interactions, and these can form a weak bond. Now that is a weak bond. However, that's important in biology. The gecko that you see here can crawl on your ceiling or your wall using van der Waals forces. On the bottom of its feet, it has these setae, S-E-T-A-E, I believe it's spelled. I'd have to look that up. I could be wrong about that, of the spelling, that is. And these setae make van der Waals interactions with the wall, and they can crawl on the wall or walk on your ceiling. So the van der Waals interactions are important in biology. Now, these atomic and molecular shapes are of extreme importance. Everything comes down to shape and conformational changes, shape changes. And without going into great detail now, because we will as we come up to it, uh, the shapes of these molecules is important. And one example is, look at this. This is an endorphin right here. All right, that's an endorphin. You make it in your body naturally. You make it and secrete it into your cerebral spinal fluid, your brain, your spinal cord, and it binds receptors. Here's an endorphin receptor. All right. Well, there's some drugs of abuse or even some pharmaceutical drugs that look like endorphins. And one of the pharmaceutical ones is called morphine. Morphine has a shape in this boxed in area that is so similar to this region of endorphin that the morphine can bind the endorphin receptor. Heroin does the same thing, but heroin is a drug of abuse. And by the way, heroin crosses the blood-brain barrier more readily than does morphine, which is probably, I'm saying probably, I'm speculating, probably one of the reasons why heroin is so addictive. It just crosses the blood-brain barrier so rapidly. Whereas when you get morphine by IV, you want to be careful because you can become addicted to it, but it doesn't cross the blood-brain barrier as rapidly. So you can see shape is everything here. So when we start talking about atoms becoming molecules by covalent bonds and ionic bonds, overall they're going to have a shape that becomes very important. All right, let's talk about some states of matter. So some physical transformations. First of all, matter can exist in a solid, liquid, or gaseous form. Only one compound exists in all three naturally on Earth, and that's water. Water can be ice, water can be liquid water, and water can be water vapor. You can see the physical transformations here, freezing and melting. Vaporization is when you change the liquid to a gas, when something evaporates, or vaporization. Condensation is the reverse. It's when a gas changes into a liquid. Sublimation is strange. Sublimation is when you directly go from the solid to the gas and you skip the liquid phase. Things that sublimate very readily is when you have dry ice, when you have solid CO2. That's dry ice, solid CO2. That doesn't go through a liquid form. It just becomes the gaseous CO2 immediately, so it sublimates. So those are some physical transformations of matter. And that's it. So the next mini lecture will be 2-3.